Okay, so I'm really thrilled to be introducing today's TILOS seminar speaker, Shirin Saeedi Bidokhti. Shirin is, I know Shirin since her graduate school days, but she's now an assistant professor at UPenn, and she's affiliated with both the electrical engineering department. She's an assistant professor in electrical and systems engineering, but she's also affiliated with CIS, the Computer Science and Information System, as well as the Warren Center for Network and Data Science. As I mentioned, I know Shirin since her graduate work at basically EPFL with a group of very well-known information theorists in computer and communication sciences. Before joining UPenn, she was a postdoctoral fellow at Stanford and Technical University of Munich. She received the very prestigious advanced postdoctoral National Science Foundation, and at Penn, she has been recipient of NSF CRII in 2019 and in 2021. She got the NSF Career Award. Congratulations! And besides her, the many accolades that prove that she's a rising star. If you look at the number of folks she has collaborated in, and the breadth of the areas she has collaborated with, you know that she's a rising star, sort of shooting up. So without further ado, I'm really interested to hear Shirin talk about the real-time sampling and estimation work that she has been doing recently. Thank you, Shirin.
Thank you, Tara, for the kind introduction. It's a pleasure to give this talk at TILOS seminar series. So I'm going to talk about real-time sampling and estimation with a focus on two application domains, real-time estimation, sampling and estimation of Markov processes in IoT networks, and testing strategies for control in disease spread processes. So to give a very broad overview of my research, with a background in network information theory, my current work lies at the intersection of information theory, networks, and learning. This particular talk is based on works with the collaborators that are shown here, with a focus on two areas of research.
Shirin, I think you are showing we are seeing the wrong set of, you know what I mean, like the screen, because we are only seeing your first slide. And if you have your collaborators' photos up or names up, we are seeing them.
Okay.
Yeah, let's see.
Maybe I can make full screen then instead. Or
do okay.
You see it now?
Okay, and then do you want to go back and forth and see if
you see my next slide now?
No. So I think what will happen is share your screen rather than the Keynote app. You know what I mean? In your stop share and share again and share your screen. This has happened to me.
Okay, so let me try again. Do you see it now? Going back and forth.
So now we only see your Keynote first.
Okay, so there are a couple of transitions that I have, so it could make it a little difficult.
You know what I mean? Like sometimes the way I do it is I share my screen and then I stop share now, share your whole screen, and then put it on play. That often works.
I can do it now. I apologize. Now. Okay, is it working now?
Yes, it works now.
Thank you for the tip. Okay, so yeah, so I was just giving an overview of my research and acknowledging my collaborators. So this talk is based on my work on timely communication in networks, as well as real-time sampling, estimation, and inference in network systems. So the work started when we were looking at Internet of Things, and in Internet of Things, the vision is that everywhere, everyone, and everything would be on the network, and for it to support various types of applications. Now, traditionally, research has focused on designing network strategies and communication strategies to maximize rate of communication. More recently, we've been looking at designs that try to achieve low latency with a particular focus on applications where safety is of an issue, vehicular networks, autonomous systems. And in Internet of Things, especially, and cyber physical systems, we also have to deal with applications where we have sensors providing information about some physical processes, and we want to have timely communication of such information for the purpose of actuation and control. So timeliness is, another aspect of design that hasn't received as much attention. And I want to talk a little bit about that first. So timeliness, which was more recently captured and quantified by the metric of age of information, looks at how timely and how up-to-date information at the receiver side is. So if you're looking at the communication scenario from the receiver's perspective, the information would be stale, or it would age by time until a new packet arrives. And at that point, the information that this packet brings corresponds to the timestamp of when it was generated at the source. So age of information as a function of time can be defined, as I'm showing in this plot here, as a function of time increasing linearly until a new packet arrives, at which point age of information or staleness of information at the receiver would come down to a point that captures how much this packet has been delayed in the network. Now, with this definition of timeliness and age of information, we're kind of disregarding information content of packets and only looking at the timestamp that they carry. And with this definition, age of information or time average age of information would be just the time average of this age function. Now, even though information content is being disregarded here, still age of information can be a good proxy when we are dealing with problems, estimation problems, especially when we are looking at real-time estimation of Markov processes, because for such processes, we know that the newest sample that we get from a Markov process would make everything that is old independent for our purposes. And if you look at the estimation error as a function of time, it would increase by time, not necessarily linearly, maybe even exponentially, but it increases as a function of time until new sample or new packet is provided at the receiver. So there are interesting connections between this metric of age of information and the actual, criteria of estimation error, and we'll touch upon that later in the talk. And, upon its introduction in 2011, a lot of work has been done looking at timeliness and its impact in the design of communication networks, how it would show up in source and channel code designs, multi-op networks, scheduling, sampling and estimation, and more recent applications ranging from, energy harvesting, databases, caching, distributed computation, and so on. So the outline of the talk is as follows. The talk has two parts. In the first part, I'm going to look at applications in Internet of Things, and I'm going to look at this at a particular application, monitoring in distributed networks. So first, I'm going to talk about age of information and designs that target at minimizing age of information. Then we'll move on to the more real question of how we can have real-time estimation of Markov processes in such networks. We'll make connections between this notion of age of information and the estimation error, and we discuss when and how we should go beyond minimizing age of information. Now, in the second part of the talk, we go beyond dealing with processes that evolve in time and look at processes that not only evolve in time, but also on a space, perhaps on a network. And in particular, we look at the disease processes, and we look at sequential sampling or testing strategies for containing spreads. So I'm going to start with the first part of the talk and introduce the application of monitoring in a distributed network. Now, suppose that we have a distributed network of sensors, M sensors, and suppose that we have a scenario where time is slotted. Now, when we are dealing with cyber-physical systems, these sensors would be sampling from physical sources. But for simplicity at this stage, let's suppose that each of these sensors have packets that are generated randomly at each time slot with some probability theta. I refer to this theta as generation rate or arrival rate of packets for sensors. And these sensors want to communicate their packets with the cloud over a wireless network in a timely manner. Now, for simplicity, let's suppose that this wireless network that is involved is just a collision channel when we have collision feedback available at the sources. For such a scenario, you would think that, well, there are various random access technologies known, such as, schemes based on ALOHA, CSMA, and so on. So why should we care about this scenario? And the answer is that all these random access technologies have been designed for the purpose of maximizing rate of communication, whereas in the example and the application we are discussing, we aim to have timely communication, and in particular, we want to have to minimize average age of information that I'm defining here. So we're looking at the age function age for all sources I at all times k. We're looking at time average of that, averaged over all the sensors. We have the expectation of it, and we have a normalization by the number of users, because we are looking at scenarios where the number of sensors is really large, and we want to disregard terms that are negligible in that. So we refer to this as the normalized age of information in this setting. And again, for simplicity, let's suppose that we are dealing with a symmetric network where all the generation rates are the same theta. Now, now that we're talking about age of information, let's go back to the definition we had for receiver's age of information and see what it looks like. So at the receiver side, age of information, which I'm showing by this blue curve here, increases linearly in time until a new packet arrives, at which point the age would drop, and this continues. We also have aging of information at the transmitter side, while new packets, at every time that a new packet is generated or a new packet arrives, transmitter's age of information drops to the value 0, and then it increases until the next packet is generated. Now, every time we have a packet received at the receiver side, the age of information drops to a value that's exactly the transmitter's age of information. So that is how these age functions evolve for this problem. And they become handy when we want to analyze aging of information in our system. Now, the first order of business is to see what are fundamentally possible. And we have two lower bounds on this normalized age of information that I'm showing here. One in terms of the arrival rate. It shows that the normalized average age of information cannot be less than 1 over theta m, where m is the number of sensors, theta is the generation arrival rate. We also have a new lower bound that relates this normalized age of information to the sum capacity of the underlying random access channel. In particular, we show that we have a lower bound in the form of 1 over 2c, where c is the sum capacity of the underlying random access channel, plus 1 over 2m, where m is the number of sensors. Now, this becomes very useful because now for every random access channel that might be of interest, depending on its capabilities, whether or not we have feedback, any upper bound that we have on the sum capacity would translate into a meaningful lower bound on the normalized age of information. And we'll see that these lower bounds are kind of relevant for the problem we discussed. Now, here I'm showing the lower bound on the normalized average age of information. Here I'm looking at normalized average age of information as a function of theta, the generation time, the generation rate. And I'm showing the lower bound in black, and just a simple stationary randomized policy where sensors just communicate with an optimized probability in each time slot. And that is shown by the brown curve. And we see that there is a considerable gap between the two, as you would expect. But the question is, well, what can we do? Now, the first thing that comes into mind is that, well, we do have feedback available. Why not go back to classical solutions, such as solutions based on ALOHA, slotted ALOHA techniques? And for those who may not remember what slotted ALOHA is, so it's a transmission strategy where sensors attempt to send their packets with probability 1 unless they have previously experienced collision, in which case they would go into a backlog mode and communicate probabilistically with a probability that can be adaptively optimized based on the available feedback and the estimate that one would have on the number of active nodes in the network. And it is very well known that such schemes are stable for small rates of theta below 1/EM. Now, if you look at such classical schemes, very interestingly, we can show that in the limit of large M, meaning that we have many sensors, when the arrival rate or the generation rate theta is smaller than 1/EM, slotted ALOHA is asymptotically optimal. So it matches the lower bounds we have, and we can also prove that its performance is given by 1/θm. And this can also be seen through the simulations we have here, where for theta smaller than 1/EM, you see the performance of slotted ALOHA is great. It matches the lower bound. It also matches centralized schemes, even though we are looking at decentralized strategies in a distributed network. However, as theta, the generation rate, increases, the performance of slotted ALOHA becomes really, really bad. And that's because, as we discussed, slotted ALOHA is not even stable anymore. Now, the question is, are we doomed in this regime where theta, the generation rate or arrival rate, is large? And is there even any benefit in increasing the sampling rate in these scenarios? If so, how can we utilize availability of fresh packets as we increase the sampling rate and we have more and more fresher packets? Now, let's look at this regime of larger arrival rates. We know that the capacity of the channel is limited, so it's not like we can hope to get more packets through the channel. However, we do have this option of deciding which packets to transmit, and we want to do this in a distributed manner. For this purpose, let me define the notion of age gain of a packet or age gain of a transmitter. So this is the difference between the age function at the receiver, the age function at the transmitter at time k. And basically what this age gain captures is how much instantaneous gain we would have by sending a packet from transmitter I. So by utilizing this notion of age gain, we can think of threshold policies where at each user looks at its age gain that it can compute because it has feedback information, and it has therefore the ability to calculate these age functions. So it looks at its own age gain. And if it's beyond the threshold, it becomes active. And if it is not beyond that threshold, it remains inactive. Now, the threshold can be a fixed threshold that we design in advance, or it can be an adaptive threshold that is time dependent, and it can utilize channel feedback in its computation. No matter what threshold policy we have, nodes can decide when to become active, and once they're active, they can transmit probabilistically, for example, like what slotted ALOHA does. Inactive nodes, however, remain silent. So let's first look at the adaptive threshold policy, where threshold t as a function of k can be computed at each time, and decision-making can then be based on that. For this purpose, let me introduce a few notations. So a node I is called an m-order node at time k if its age gain is equal to m. Then we can look at the fraction of nodes of a certain order m, denoted by LMK. And then we can look at the profile of these fraction of nodes of different orders, and we refer to that as the age gain distribution. Now, we use this age gain distribution for the purpose of designing our adaptive threshold policy. And for this purpose, we need to have an estimate of this age gain distribution, and we do that as follows. So suppose that at time k minus 1, we have an estimate of the age gain distribution. Then from that, we can compute the expected fraction of nodes that have just become M order, and that would be useful in designing the threshold so that the effective rate would be just beyond what we know we can support, which is 1 over EM. From this estimate, we can update our estimate of the age gain distribution upon generation of new packets, and we can utilize the collision feedback in order to update the age gain distribution for time k, and that would feed back into the loop to allow us to compute the threshold at time k plus 1, and so on and so forth. It's relatively straightforward to find closed form formulas for these expected fraction of nodes that have just become M order, and also the updates that we can get for the estimates of the age gain distribution. So I don't want to go into all the details there, but I want to show the performance of such a policy where the threshold is computed adaptively using the collision feedback. So here, the red curve here shows the performance of our adaptive age-based policy. As you see, it is optimal as expected for small generation rates, rates below 1 over EM. And furthermore, it decreases as theta increases, showing that it's able to utilize the availability of fresh packets, and it shows that the normalized age gain decreases as the generation rate increases. So this is a considerable, it shows considerable gain compared to state of the art, as we discussed before. We can also provide analysis for the fixed threshold policy. Here we want to design an optimal threshold T star, where again, nodes can decide whether or not they would be active. So this T star is designed in advance, so it's independent of the collision feedback. We can get a closed form for T star in terms of EM minus 1 over theta plus 1. And we can show that for generation rates that are not too small, in the limit of large M, this normalized age would be E over 2. If we look at the normalized age again as a function of theta, the blue curve here shows the performance of this fixed threshold-based policy, and it shows an improvement of factor 2 compared to, again, state of the art. Now, let me just say a few words about this theorem and how we go about proving it. So the idea is that, again, we are looking at age normalized by M. So we are disregarding terms that are negligible in M. When theta, the generation rate, is not too small, we can argue that the contribution of the arrival rate is negligible, and the main contributor is the age gain of the delivered packets. Then we can show that the expected age gain distribution on nodes converges to a uniform distribution on orders 1 to up to T star. And then we can argue that active nodes are almost all of order T star. This is order M, however, their fraction is vanishing. And therefore, at the end of the day, we can prove that the normalized age gain would be converging to E over 2, which is 1/2 what we would have utilizing, let's say, scheme-based slotted ALOHA. And let me also mention that all these techniques and all the strategies and all the results remain valid when we consider any other random access technology, including CSMA. So we can, again, generalize the results in a similar manner and get a factor 2 improvement on the performance. So here I'm showing the performance of what could be achieved by fixed threshold-based policies for a random access channel with CSMA capabilities, and that is shown by the red curve or the purple curve here, and it's almost matching what we would have by a centralized policy. Again, just because we have CSMA capabilities in that scenario. Let me at this point stop for a second and ask if there are any questions before moving forward.
Perfect timing. I had a question. So, Shirin, there has been some work in, and not necessarily related to age of information, just classic queuing delay, where folks have talked about, like, I think this is as old as the slot in ALOHA itself, as sort of thinking about almost like creating a CSMA, even if you don't have the sensing capabilities, you collide, and if you get on a much faster time slave, you collide, and then depending on what happened to the outcome of the collision, you get a reservation of a longer time slot to transmit. And those are shown since you are basically generating common randomness in this collision channel, right? So then you can sort of, at the end of the day, when things get really busy, you sort of converge to a TDM mode because you're just getting unique numbers generated for your reservation piece. Do you think that kind, I mean, and of course there, the idea is that you just want to deliver every single packet. So this is a sort of a very different paradigm here. Is that something that you would expect you will get a similar result if you just add that? It sounds like you should, right?
I think so. So as long as the random access technology you're talking about does not involve any coding, and I personally am not aware of such a random access technology, the ideas and the proof should go through. And just
in some ways you can sort of think of it as coding, right? Because there are these two type of time slots, the very narrow ones and the really big ones. So you can sort of think about your code, like the very tiny ones are the parts where your coded information, and in its feedback, right? So it creates some common randomness. So it becomes like a MAC channel with feedback, but in very weird kind of feedback, not a classic full feedback scenario. And then you use that to sort of code, and you can sort of think about TDMA as a very, very silly MAC code, but it does a good job for collision channels, right? So in that sense, it's a little bit like that.
Mm-hmm. So
and then there are some coded ones, right? But their channels are not collision, right?
They're not collision.
Fading channels.
Yeah. That's true. So I think maybe I should look at the random access technology that you are, like the technique that you're mentioning, to just make sure that this would.
I think your analysis honestly will go through. I don't think Nobody was looking at age of information. I'm talking about like, I don't know, like in the 80s or something, that the first results. I think Jean Morin had a very clever version of it back in early 2000s. That is worth looking at.
Yeah, I mean, let me look at
that. But I think your analysis will go through nicely, and I don't know how it will do in terms of age of information, because TDM schemes are pretty bad with age, with delay short term. So I don't know where it cuts, right? Like it will.
Yeah. So the problem with TDMA-based policies is like they're centralized, right? And we want to have decentralized strategies. So that's,
if you have common randomness, you can do like you could just do TDM with decentralized common random. I mean, like it's a fake way, but the feedback in the channel, right, gives you. I mean, even classic multi-axis channel with feedback, all you're doing is generating sort of a way to create a collaborative, like, user-based codes, right?
Yeah,
like
exactly, because of the channel feedback. That's true.
Yeah.
I think just because you brought it up, it's it is true that based on the policy you have, you may be able to provide some kind of coordination among the nodes. Actually, if you look at the adaptive age-based policy that we have, the red curve, you see that it goes below what we would have as E/2. And if you look at the lower bound, we had this 1/2C that would say, well, if we were building on a slotted ALOHA type of strategy, even though we had this, age-based thinning of the process, how can we go below that point of E/2? Isn't it a case that the capacity on their slotted ALOHA would not be above, 1/E? And the answer here, what we found out is that because of this utilization of the channel feedback, we are actually not doing a slotted ALOHA anymore. We are kind of creating some sort of coordination. We are implicitly improving rate of communication while reducing the age. And the effective channel capacity at this point would be comparable to the ones that kind of utilize or create some sort of coordination among the nodes. So in this sense, it's very interesting for me to know more about the scheme you were suggesting to just understand better what type of cooperation utilization of age is providing and how that can be improved, right?
One more comment, just because this is a sort of a bigger audience of folks who are interested. There's also this really cute connection to this problem of random number generation, right? So one way of thinking of slotted ALOHA is, as you said, is a probabilistic axis of the channel. And one way you can realize it, and this is how it's realized in like Wi-Fi or whatever, is pick a random number generator, count down to it. When the number count hits, you transmit, right? So this view is sort of equivalent. And so that translates, in the max scenario, people were thinking, if I have common randomness, or if I have feedback to generate the common randomness, what is the best strategy to guess the smallest number, the smallest unique number that I choose among the group? So you have M users, they all pick a random number between 1 and, let's say no upper bound, or you could put an upper bound. And the one that is picking the smallest one sort of gets to go if there's no collision, right? So that sort of ends up being a very cute probability problem, So I think that's, but then again, it's all the questions are around, the delay to deliver the first one or rate. This is really clever to think about age of information in that setting. I think it's a really cute result.
Thank you for pointing it out. Yeah. So, so as so far we talked about how we would design these, communication schemes or basically network strategies to minimize age of information. And so far, we just disregarded the fact that what these sensors have are coming from some underlying physical processes. Now, we want to go back to the original problem that we had, and that is when you have sensors that are perhaps sensing or sampling some physical processes. And the goal is not to minimize age of information. So it is actually to minimize the estimation error. So at the cloud, we want to have a good estimation of all these Markov processes that we assume to be independent in this setting. So at each source I, now let's suppose that we have a Gauss Markov source with the innovation process being W, Gaussian, zero mean, variance sigma squared. And the goal is to minimize the estimation error, looking at the difference between X, the source at time K, its estimate at time K, again, time average over all the sensors. And we again further have a normalization by M to look at the case where the number of sensors is very large. So the question is, how can we design distributed sampling and communication strategies? Now, intuitively, one would think that, well, perhaps age-based policies are sufficient. They are trying to facilitate timely communication. And we know that for Markov sources, that's what we want. We want to have the newest packet, as soon as possible to have a good estimate at the destination. However, it's not as clear because we were disregarding the information content of packets dealing with age of information. And here, when we're talking about estimation error, perhaps that should contribute as well. So in order to answer these questions, we look at two classes of policies. The first class of policies are the ones where decision-making does not depend on the source realizations. We call these oblivious policies. And the second class of policies are policies where decision-making can actually depend on the source realizations as well. So these are not what we call non-oblivious policies. Now, if we look at the average estimation error, and in particular, if we look at the estimate of xi at time k, for our problem, that would be the source at an earlier time, and that would be the generation time of the last packet that was received from source I. And if we look at this difference now, that would be a sum of these innovation processes, these noise processes, WIK. And how many of them? Exactly HI, the age at time K with regard to source I of them. So once we see that, we can prove that in the class of oblivious policies where decision-making does not depend on the source realizations, the problem of minimizing estimation error just directly reduces to the problem of minimizing age of information. And the estimation error would be the average age of information times sigma squared. So everything we discussed earlier on for minimizing age of information directly applies here and provides strategies for minimizing estimation errors. However, if you look at the more general class of policies where decision-making can depend on source realizations, we don't have this equivalence anymore. And as a matter of fact, we can go beyond that. We can utilize what we can learn from what we saw for age minimization and propose policies that instead of working with the age functions, works with the error process. So the error process is defined here. It's just the error process, as you would expect, the difference between the source and its estimate at time k. And this is something that each node can compute because of the availability of the feedback. And then each node can look at the error process. And again, we can devise policies that are threshold based. Here, threshold is denoted by beta. So nodes become active when the error process crosses threshold beta, and they would remain inactive otherwise. Now, in providing an exact analysis for this problem turned out to be very, very difficult. And at the end of the day, we were able to prove approximation results. So by approximating our process by a winner process, utilizing stopping time results for winner processes, we can show that an optimal choice for this threshold beta would be approximately sigma times EM. And under this choice of threshold, the estimation error would be E over 6 over sigma squared. That would be a factor 6 improvement on what state-of-the-art strategies would attain. So here we have state-of-the-art in green and brown, fixed threshold policy, which minimizes age. In terms of estimation error, it would have the performance shown by the blue curve. The adaptive age-based policy is the red curve. And here I'm showing the estimation error as a function of sigma squared. The red curve is the approximation we get for the performance of this policy we proposed. The black curve is the actual performance that we can find by simulations. And the yellow curve is what we could get by a non-oblivious greedy scheduling, which is assuming that we have coordination among the nodes. And this shows that, this distributed policy performs really well. It gets very close to what, a greedy scheduling would let us get to. So this ends the first part of the talk. We discussed.
Sorry, Shirin, just one quick question. I'm sorry, I don't want to slow you down, but this is really interesting. Do you know, I don't remember the exact setup, but I think Ashutosh, God, I'm just completely spacing out at USC, my academic brother, during his postdoc with Venu Verbali, looked at this sort of a problem of estimation. And I believe they did like almost like a dynamic program. And I believe something like what you have, they proved that it's optimal. I think it's maybe point-to-point setting. So the setup is a little bit different from yours. So there's a sensor that is observing the observations, and then there is a node that is not at the sensor, but decides to pull the sensor. And the question is at which point it should pull the sensor. And it works on sort of like a belief about what the sensor is producing. And then they had a really nice, it's very surprising, but they have optimality results for certain class of Markov policies. I don't know if you...
Point channel?
I think they had both point-to-point and multi-user, but I don't remember the details. I think the original work was Nuno Martin's work. He had shown some simple version of the problem, and Ashutosh managed to generalize it to pretty general processes, so long as they have some symmetric properties. Mm-hmm. So it's something to note that that they had some proof that maybe this is the best that you can do. And it was a very surprising, because in these MDPs, POM-DPs, it's hard to get any kind of results, and finding the optimal was very surprising, a very beautiful result. They were working on self-modularity of the belief. So I think it would be,
I have to check it out.
Yeah, check it out. Again, it was not age of information, it was estimation. And I don't remember what they defined to be the estimation error and things like that, and what was their estimate. I mean, right now you're doing a point estimate. They were doing something like a Bayesian filter. But it's worth looking at, I think.
Yeah, thank you. Yeah, sure. I'll check it out. So any other questions for the first part of the talk? Okay, if not, then let's move on to the second part. I'll try to be a little faster given the time. So far we discussed processes that were Markovian in time. But an interesting question would be, what if we have to deal with processes that not only evolve in time, but also on the space, perhaps on a network that is defined? And that kind of matched very well with the questions that, are of importance these days about testing and control of, disease processes such as COVID-19. So for this purpose, suppose that we now want to define our disease process. So the state of a node would be perhaps the state of the disease. So denoted by sigma IT. I refers to the node I, and T is the time. Now we have evolution in time. That would be different stages of the disease. Perhaps we are susceptible, then we are in the latent state, infected, and then recovered. That's a very simple model that we consider. It's a compartmental model. We further have the spread in the network, which means that the state of node I at time t plus 1 is probabilistically determined by the state of the nodes at time t, which were in the neighborhood. That would be defined by the underlying network. Now, we want to design testing and isolation strategies. So again, at node I, the state is sigma IT. Once we test a node, we will get an observation about whether or not this node is infected at this time. And based on that, if a node is tested positive, it goes into isolation. So we don't design the control policy, it's determined. Once you test, if it's positive, we have this control policy of isolation. And the question is who to test and isolate given some limit on the daily budget. So it can be time dependent or it can be fixed. And the idea is to see if we can minimize the cumulative infections. And that cumulative infections could be written in terms of sum over time, sum over the nodes of what would be the probability of a node being infected. Now, there are interesting challenges in minimizing the cumulative infections here. So on the one hand, looking at this formula, we want to minimize probability of infection by just isolating infected nodes. That's how it would contribute. But the fact is that we don't actually know the probabilities of infection of the nodes. So testing would serve two purposes. One is to get a better estimate of these probabilities of infection. The other is once we get a positive result, we get to isolate them and contain the spread. So if somehow we knew what these true probabilities of infection were, then it's relatively straightforward to argue that a myopically optimal policy would be to just test the B most likely nodes to be infected, and that would be myopically optimal in a class of policies where decision-making is, given the probabilities of infection, is independent of the network topology. However, what happens is that we actually don't know these true probabilities of infection. We may have no idea of how the disease has spread so far and who is infected and who is not. So we have to have some way of estimating probabilities of infection. So this means that we would have some belief about probabilities of infection. The true probabilities of infection are U, but we would have, and we would want to form a belief about these probabilities of infection that would be sequentially formed based on the history of test observations. That we denote by U. So U's are kind of estimates or our belief about the probability of infection of nodes at different times t. What we do is that we update this belief sequentially based on our test observations. Now, suppose that at time t, we have some estimate of probability of infection of different nodes I. We are going to make our decision based on this belief. We're going to test some nodes, and based on those observations, the at first glance, one would want to utilize these observations and make a guess about who else in the neighborhood might have been impacted. But the fact is that we have to go beyond that. We have to first go back in time, update our belief about probabilities of infection at time t minus 1. And if we had we didn't have any constraints on limits of computation, we would want to do this, go back in time forever. For our purposes, we just go back one time slot in time and then propagate that impact in time at time t and time t plus 1 to get an estimate of the probability of infection at time t plus 1. So then again, at time t plus 1, this is used for decision making to see who is going to be tested. We have to propagate that back in time, update our belief about a probability of infection in prior times and feed that forward in time to get an estimate for probability of infection at time t+2 and so on and so forth. So we have a kind of a message passing that is done back and forth in time, and we can provably show that this backward step is necessary. So I'm not going to be able to discuss the details of it here, but it is essential to have the backward step as well, as you can imagine. So once we have these estimated probabilities, one would say that, well, now let's pick the B most likely nodes based on these estimates of probabilities of infection, U, rather than the true probabilities of infection, V. However, the question is, are such exploitation-based policies good? Is it a good policy to make decisions based on these estimates of probabilities U that we have? We can show through a simple example on a line network that, as a matter of fact, exploration may be necessary. So what this means is that we can show that with a high probability. This is just a number that you can make it as high as you want. The total cumulative infections under exploitation policy that we discussed is alpha over n, where alpha n being the number of nodes, alpha being a constant. However, if we, in addition, add some sort of exploration, perhaps through random testing with a part of the budget, we can already reduce the cumulative infections to alpha n over 5. And again, this 5 is just a constant. We can make it work for any constant here that you wish. And this shows the necessity of exploration in such, in this problem, just because, decision-making based on the estimates that we have found would bias our decision-making into what we have learned so far, and we would be missing out on, parts of the network that we just haven't tested so far. So, for this reason, we look at exploration-based policies that are based on posterior sampling. We look at two scenarios where the budget is time-dependent. Perhaps it's equal to the expected number of infected nodes, or it could be constant, independent of time. So in the first case, we would test each node I based on its probability of being infected. So this way, we won't miss out on nodes that may have a small probability of infection just because, we haven't learned about their probability of infection yet. In the second case, we just have to scale these probabilities to meet the budget as expected. So I want to show some simulation results before concluding. Here I'm showing some simulation results for Watts-Rogatz networks of 200 nodes, degree 4. The top part shows the case when we don't have any rewiring probability. So these are like really clustered. What you see is that the black curve on the top is what we would have with no quarantine. If we just do random testing, we get the blue curve here. If we do contact tracing, we get the purple curve here. If we do time-dependent exploitation-based policies, we get the light blue curve. And if we do time-dependent exploration-based policies utilizing posterior sampling, we get what we see here as the red curve. We can also look at the daily finds, and this shows that exploration helps find more positive results earlier on. And by doing that in a timely manner, helps contain the disease much better. We also see here in the third plot that the error that we have in estimating the probabilities of infection goes down when we utilize exploration-based policies. And this is not the case if we just stick to exploitation-based policies and working with the estimates of probabilities as if they were the true probabilities. Now, the results remain consistent when we look at different rewiring probabilities. However, the gain of exploration decreases as the rewiring probability increases, the path length decreases, the clustering decreases. And that is something that we have consistently observed in various networks. We also looked at real data networks. So this is a network that we could construct from data that was collected from smartphones of university students as a part of the Copenhagen network study. So looking at the cumulative infections, we see again how the cumulative infections, how large it would be without any testing or quarantine. Here, the blue curve shows random testing. We have contact tracing as the purple curve. Light blue shows time-dependent exploitation. And the red curve shows the performance of our proposed time-dependent exploration-based policies. And again, we see that exploration provides a little better estimation error of the probabilities of infection, but not as much as we saw for the Watts-Ragaz network. So with this, I want to conclude my talk and stop and answer any questions that you may have. Thank you.
Any questions? I know that Andrew and a few others had to drop off because of time coming, but Nima, your hand is up.
Yeah. Sorry, I didn't want to interrupt. But yeah, this is very exciting work. For these last results, are the networks assumed to be static throughout the duration of the simulation, or are they allowed to be dynamic?
The first set of simulations, they're static. The second one, they're dynamic. So it could be dynamic, and nothing changes because of the way that the policies work.
Perfect. Very interesting. Thank you.
Thank you. This was a fantastic talk, Shirin. I know that we just hit the 11 and many people have teaching in other classes and stuff, but this was fantastic. If I recommend if folks have questions, they can direct them to Shirin through the TILOS channels that we have, or in fact her email address. And with that, I would propose that we end the talk. So Shirin, again, thank you so much. This was an excellent talk.
Thank you so much, everyone. So yeah, please reach out if you had any questions. I would be very happy to talk more. Thank you.
There are many comments and compliments in the chat. Thank you again.
Thank you.
Have a very good day all.